Hey everyone, welcome back one more time, and thank you for joining us again as we open up the discussion on the inference about two population standard deviations. Heading into our first objective then, if sigma 1 squared is equal to sigma 2 squared, and s1 squared and s2 squared are sample variances from independent simple random samples of size n1 and n2 drawn from normal populations, then we're actually presented with this new statistic that is our F statistic. Our F statistic follows the F distribution with n sub 1 minus 1 degrees of freedom in the numerator and n sub 2 minus 1 degrees of freedom in the denominator, referring to sample 1 and sample 2 of course. We see the graph over on the right looking very similar to our chi-square distribution that we've worked with before, but again this is a new distribution for us so far. It is the F distribution. And that's what we'll be working with as we head into our section. Heading into our objective then, hopefully this is feeling a bit familiar as we do have requirements that need to be satisfied in order to conduct the hypothesis test. First, our samples need to be obtained using simple random sampling. We have to have independent samples this time, and the populations from which the samples are drawn need to be normally distributed. Note that it is not enough to have a large sample. We don't have something that helps us out in that manner. The samples must be checked using a normal probability plot, regardless of the size of the samples, unless we're flat out told the population is a normal distribution. And then we see some notation there at the bottom of the screen. That's just to keep everything lined up, since sometimes sample variance and population variance can be a bit confusing. But let's go ahead and jump into the steps on conducting these hypothesis tests. First would be our null and alternative hypotheses. And just like we've seen with hypothesis tests about population means when working with independent samples, this time we have sigma 1 equal to sigma 2 as our null hypothesis, as opposed to mu 1 equal to mu 2. Again, independent samples though, we see this sigma 1 versus sigma 2 with the correct relationship corresponding to the type of test that we're conducting. We have alpha again, that's usually set for us. Remember, alpha is the probability of making a type 1 error. Heading into the details of the test, we calculate the test statistic, which is F naught. And this of course being one of the happiest formulas that we have for a test statistic, since all we're doing is working with the sample variances. Once we have the test statistic, we need to find the corresponding p-value, but note this time we're using the FCDF function, as opposed to the normal CDF or the TCDF function. Remember, we're working with the F distribution, and our calculator has an FCDF function. Similar to the TCDF function, we do have to address that we need to work with degrees of freedom, but make sure we take note that we need to pay attention to the degrees of freedom in the numerator and the degrees of freedom in the denominator when working with our FCDF function. And like we've seen before, if we have a two-tailed test, we need to make sure we double the FCDF results. And finally, one more time, if our p-value is less than alpha, then hopefully by now we know we need to reject the null hypothesis. Now just one extra note, it's a technical aspect for real-life stats, but not an issue in the classroom setting. The procedures presented are not robust, and that means minor departures from normality will adversely affect the results of our test. Therefore, the test should only be used when the requirement of normality has been verified. We've kind of said that already, but again, just a technical aspect that we're presenting for the sake of a real-life stat situation. But let's go ahead and jump into our first example then. Well, taking a look at our first example then, we're heading back to the state quarters versus the traditional quarters, as seen in a previous example. But this time a researcher wanted to know whether the state quarters has a standard deviation that is less than traditional quarters. So we're not talking about mean weights this time, we're working on the standard deviation, and that's something we want to emphasize to make sure we recognize what parameter we're addressing. He randomly selects 18 state quarters and 16 traditional quarters, weighed each of them, and obtained the following data, so they give us the data of course. They tell us a normal probability plot indicates that the sample data could have come from a population that is normal, and then we're told to test the researcher's claim at the alpha equals a 0.05 level of significance, given the following data. We'll note that the test requirements are met from the given information in the problem, since of course we have an SRS, and the normal probability plot said that we're good to go. Heading over to the data, if you don't have it in your calculator already, we're going to throw the state data into L1, and the traditional data into L2, but then going back to the original story, just to make sure we have this lined up correctly. The claim is that state quarters has a standard deviation that is less than the traditional. So that means we're saying that our L1 is going to be less than our L2. Well, if that's okay, then we can head into our hypothesis test setup now. First, our null hypothesis, which we know would be sigma 1 equal to our sigma 2, since we're discussing the standard deviation. A little more careful on the alternative hypothesis though. We have sigma 1 less than sigma 2, since we're saying that our state is less than traditional, and we call it state sample number 1. If we're okay with that, then that means we're ready to calculate our test statistic, as we know our level of significance is already a 0.05 as given from the problem. But to calculate the F statistic, we need the variance from each of our samples. Well, to do this, we could use the 1var stats function on our calculators, or we could jump to the calculator portion of our notes, like we've been doing in previous sections. Well, jumping to the calculator instructions, we want to conduct a 2-sample F test on our calculators. Again, remembering we're conducting a hypothesis test on standard deviations. Well, we see the instructions on how to conduct the 2-sample F test, so let's go ahead and take a look at the calculator. Taking a look at our calculator, like we see on the notes, we need to hit Stat, arrow over to Test like we've done plenty of times so far. I'm going to hit the up arrow just to skip down to the bottom, and we see option E on my screen would be the 2-sample F test. We'll hit Enter to go ahead and enter the test. Remember, we put our data into L1 and L2. Like we've seen before, if they gave us the stats, we'd be using that. But instead, we have the raw data for our 2 samples. So list 1 is L1, list 2 would be L2. Our frequencies would be 1 each. Remember, our alternative hypothesis would be less than our sigma 2, and we can hit Enter on Calculate. After hitting Enter, we get the output from the test with a whole bunch of information. First, just taking a look, we have the F statistic, which is what we're trying to find right now. We have our p-value, which we know to apply toward the results of our hypothesis test. But what we want in the moment for a free response situation would be the fact that now we have the sample standard deviation for each of our samples. Which means as long as we're okay with the calculator, we're all set to head back to the notes in order to show all the math in a free response situation. Back to our notes then. From our calculator, we found S1 to be a 0.0497. We found S sub 2 to be a 0.0689. So we can substitute those to find our F statistic. Remember though, those were our standard deviations. So like that formula says, we need to square each of those as we're working with the variances. Well, if we do this by hand and input these values into our calculator, we've actually rounded to only 4 decimal places, of course. So we end up with an F statistic of approximately 0.5203. Now, just to be clear, from our calculator, our F statistic was slightly different. Nothing to worry about, just a result of rounding error. So make sure you know either way is okay. If that's okay, then our next step would be to find our corresponding p-value. Well, to find the p-value, we need to use our FCDF function. Remember, we have a left-tailed test, so that means our lower bound would be our negative 10 to the 99, up to our F statistic, that would be a 0.5203. Remember, next we need to input our degrees of freedom, which would be a 17 and a 15. And remember, that would be the degrees of freedom from our numerator and the degrees of freedom from our denominator, where we had a sample size of 18 in the numerator and a sample size of 16 in the denominator, coming from sample 1 and sample 2 respectively. If you input that into your calculator, we get a p-value of approximately 0.0982, and from there we're right back to what hopefully feels comfortable in our hypothesis test. As we know, we're comparing our p-value to our alpha level, and since our p-value is greater than our alpha, we know that we do not reject our null hypothesis. And of course that takes us to our conclusion. Hopefully we're comfortable by now with our conclusions of hypothesis tests. Because our p-value was greater than alpha, we know our conclusion would be that there is insufficient evidence to conclude that the standard deviation now of weight is less for state quarters than it is for traditional quarters, at the alpha being a 0.5 level of significance. And we're all set with our first 2-sample F test. Well, that takes us into one more extra example, just to make sure we're hopefully comfortable with our hypothesis test on 2 standard deviations. Taking a look, we have a randomized experiment where 150 babies were randomly divided into a treatment group of size 75 and a control group of size 75, where they told us that they're calling the treatment group sample 1, denoted by N sub 1, and the control group would be our sample 2. After the study, the treatment group had a mean serum retinol concentration, which is not the easiest to say, of 49.72 with a standard deviation of 17.81. The control group had a mean serum retinol concentration of 13.84 with a standard deviation of 12.37. The point of saying all that is after all that confusing information, we see the sentence that helps clarify what we're actually trying to accomplish. We're asked, does the treatment group have a higher standard deviation for this concentration than the control group, at the alpha being a 0.5 level of significance? As soon as we see higher standard deviation, we know to head into our 2-sample F test, especially when they tell us to assume that the concentration is normally distributed. So we're all set. and we get to jump into our hypothesis test. Well, now this example looks a lot closer to an exam question because we've got just a blank page after our actual question. So we have to know, the first thing I need to state would be my null and alternative hypotheses. That is, we need to address H0 and H1. Since we're testing standard deviation, H0 would be that sigma 1 would be equal to sigma 2. And since the question asks, does the treatment group have a higher standard deviation than the control group, that means we're going to call this a right-tailed test since our treatment group is sample 1 and the control group was our sample 2. Well, if we're all set there, we get to go straight into our F statistic then, which we know would be the variance from sample 1 divided by the variance from sample 2, and they gave us this information. We were told in the story that we had standard deviations of 17.81 and 12.37. Just make sure we use the standard deviations and avoid the distraction that would be the mean values from each of those samples. So our value of S sub 1 would be that 17.81 and S sub 2 would be the 12.37. But as seen in our previous example, we want to make sure that we draw attention to squaring each of those values because we need to input the variance, but we were given the sample standard deviations. Well, if we input that into our calculators, we end up with a test statistic of approximately 2.073, and we're ready to find our p-value. Well, now that we have our F statistic, we know to use the FCDF function, but this time we have a right-tailed test. So in our FCDF function, we have a lower bound of a 2.073, which was our test statistic, going up to our positive infinity, and then the degrees of freedom in both the numerator and denominator would be 74, since we had the same sample sizes for each of our samples. If that's okay, our output would be a 0.000996. Now our calculator would probably say this 9.95, etc., e to the negative 4. Just a reminder that our calculators would be giving that in kind of a scientific notation, and I just wrote it as a normal decimal. And that means we have our p-value, that is that value of approximately 0.000996. We know to compare that to our alpha of a 0.05, and we are quite clearly less than alpha, and we know that means we get to reject our H0. And that of course takes us to our conclusion. One more time, since our p-value is less than alpha, that means there is sufficient evidence to conclude that the treatment group has a higher standard deviation for our concentration than the control group at our alpha being a 0.05 level of significance. Just drawing attention one more time, we brought in the alternative hypothesis with that word that is higher, and then just highlighting the fact that we're conducting a hypothesis test about the standard deviation. And that wraps up our discussion on the inference about two population standard deviations. Thank you one more time for joining us.